Okay, so I have a question on the board here, not in your packet, but just a question we can answer nonetheless. It says, for what angle theta does sine of theta equal 1/2? And I know I could give it an answer in terms of radians, or I could give an answer in terms of degrees, but there should be lots of answers that are popping in your head that could make this true. Think of any kind of angle you could put in the, anywhere in the unit circle who has a positive 1/2 ratio. So like maybe over here, sine of what angle is that? Like what angle would have that ratio? Well, you could think of it as 30 degrees or pi over 6 radians. That would be a solution. But there's nothing that says you can't be over here as a reference angle of 30 degrees in quadrant 2. And that would also satisfy that equation. So you could say 150 degrees or 5 pi over 6. Or as you start to think about, well, really, any coterminal angle, so I could either add 360 degrees or subtract 360 degrees, anything that lands on those two principal values would satisfy this equation. Okay, now another way to look at that equation, or to think about that. If I said theta equals inverse sine of 1/2, or some textbooks use this notation, arc sine. And I'm going to use both notations. Our current textbook uses this. Next year when you get into calculus, you'll use arc sine. They both mean the same thing. They both are looking for an angle whose sine ratio is 1:2. 1:2. What I like about this notation actually a little bit better than this notation is that there's no ambiguity, there's no inverses here. Reciprocals, because often the -1 as an exponent could be thought of as the -1 power, which means take a reciprocal. But not true for here, because we already have a reciprocal defined for sine, it's cosecant. So this helps us actually to hopefully avoid that ambiguity. But also, it refers to if you have an arc on the unit circle who, when you construct that angle back down, has a sine ratio of 1:2, what is that angle? So it also gives a nice geometric reference to where that name came from. Now, the answer to this is both either 30 degrees or pi over 6, but that's it. And there's a difference between these two problems and the previous one. And the difference is that when solved for theta, when the inverse function is already embedded in your problem, there's a restricted domain. And if it's not there, like in the first one just said, it was just the normal sine function, not the inverse sine function, the arc sine. If it was just a normal sine function, then any answer that you could possibly think of to make that a true statement would be a valid answer. Here, it's limited to just one. And it's very similar to thinking about an algebra. The difference between, is the square root already there, or do you have to introduce the square root? If the square root's already there, it wants just one solution. It wants the principal root. It wants x is equal to 5, the principal root. If I have to introduce a square root to my function, to my equation, if I'm introducing that square root, then I actually need to think about that as that's the absolute value of x is equal to 5, or x is equal to plus or minus 5. I get two solutions. So same idea here. If you already have the inverse function, if it's already part of your problem, there's only one answer. There's a principal answer. Now the question is well, how do you know what the principal answer is? Because is it the positive? But you had two positives, so how do you decide? So there has to be a way that we're going to define these inverse functions. Where will we put these angles? In which quadrants should we limit them so that there's no ambiguity? So when I say, inverse sine of 1/2, I know for a fact it's pi over 6. I'm not thinking about its second quadrant representation of 5 pi over 6. I'm not thinking about anything else other than this one. And so that's where page 24 comes into play. Page 24 of your workbook is what I like to call the geography. Where should we put these angles? And these are how the functions are defined. So it's not just Mr. Brown, right? It's not just Mobile 5 math. This is how they are defined. So there are 4 quadrants, and the positive angles will always exist in quadrant 1. So anytime you have arc sine, arc cosine, if it's a positive ratio, arc tangent, if it's a positive ratio. Notice I'm putting arc, the same thing as inverse sine, inverse cosine, inverse tangent, then arc cosecant, gotta check the C's there, arc secant, and arc cotangent. Okay, so when you have a positive ratio, if you are given a positive trig ratio and you're asked to find what angle has that ratio, and it's a positive ratio, then it's in quadrant 1. That's easy. Everything's positive goes into quadrant 1. Now, if you have a negative ratio, then we split. So the ones that are defined in quadrant 2 would be arc cosine of a negative ratio, arc secant, which is reciprocal of a negative ratio, and then arc cotangent of a negative ratio. So 3 of them will exist over here in quadrant 2. If it's a negative ratio, you would draw an angle in standard position and you would put it into quadrant 2. And notice that in quadrant 2, what is negative about it is this piece right here. That x has a negative value. And so that sort of makes sense that cosine and secant would be defined here because they depend on the x. Cotangent depends on both the y and the x. So in this case, cotangent I'm putting in quadrant 2, notice its reciprocal function's not up here. Tangent, which depends on y and x, if it's negative, we're actually going to put down here in quadrant 4. So then if I'm the other 3 values, so if I'm arc sine of a negative ratio, arc cosecant of a negative ratio, or arc tangent of a negative ratio, I'm going to put them down in quadrant number 4. And again, I would start in standard position, and I would go this direction to get to quadrant 4. So notice again that these triangles, they would have a negative y value, which sine and cosecant depend on. Tangent could have gone either way, and so we put tangent when it's negative is here, cotangent positive is up here. Okay, now notice what's missing, quadrant 3. So you're never in quadrant 3. So that's good to know. Then the other thing to think about is your range of values, your output. If you're a quadrant 1 and 2 angle, so if you're a arc cotangent, arc secant, or cosine, it's a little bit more natural that you would be in a continuous range of values. So from 0 all the way to pi. So that would give you a nice smooth continuous output of values. So they will range from 0 to pi, or 0 to 180 degrees. 0 to pi, okay? Now, if you're a quadrant 1 and 4 function, like sine, cosecant, tangent, you need to be a continuous range of values. So you're not going to start with 0 to 90 and then skip, and get to 270. You're actually going to start down here at the base at negative 90 and go up to positive 90. So that's the continuous interval we go from there, from negative 90 up to positive 90. So that's a little, again, difference, negative 90 degrees to positive 90 degrees, or from negative pi over 2 if you're in radian mode to positive pi over 2. So that's the difference. The angles that are in 1-4 angles could be negative as an output. The angles that are 1-2 angles could be obtuse as an output if the ratios are negative. Okay? So like when you start solving these problems, you're going to start to think like, wait a minute, I've done this. I did this last chapter. And you kind of did. We're just going backwards. Instead of saying, give me the sine of 30, saying, here's a ratio, what angle gave you that sine? So, and this is like our very first problem, the warm-up problem, inverse sine of 1/2. Here's how I would tackle this. I'm noticing it's a positive ratio. Everything is positive, or everything that's positive goes in quadrant 1. So a 1-to-2 ratio, there's my theta, and I want to think, okay, who is this? What angle has a sine ratio of 1 to 2? Well, that angle is pi over 6. And because the inverse function, whether it's the sine to the negative 1, which we read inverse, or if it was like an arc function, you know, if that's given, then it's the principal root or the principal angle, so it's quadrant 1. Here, inverse cosine of negative root 3 over 2. I'm noticing it's a negative ratio, so now I've got to remember they split. Some of the negatives come up here, some of the negatives go down there. If it's cosine, it's a quadrant 2, so that's just, again, one of those things that I'm going to have to make sure I remember the geography of the inverses. You know, I'll refer that to class, like, here's the geography of the inverses. Where are you drawing these angles? Is it a quadrant 2 angle when it's negative, or is it a quadrant 4 angle when it's negative? So cosine, I would draw negative root 3 to 2, here's a 1. And again, I think about, okay, well, that's a 30-degree reference angle, but it's a 30-degree reference angle in quadrant 2. I'm looking for this obtuse angle. That obtuse angle is 150 degrees, or 5 pi over 6. Okay. Inverse sine of negative 1. So again, thinking about it, sine as being negative. Sine is negative down in the 4th quadrant, down here. And I need the opposite to hypotenuse to be a 1-to-1 ratio. Well, this is one of our fake triangles, or like our imaginary triangles, a triangle that collapses. So if you go 0 in this direction, and you're basically just straight down, well, like that's 270 degrees, but that doesn't fit the range of our values here. Remember, we're only going from negative 90 to positive 90, so it's negative 90 is the principal answer, or negative pi over 2. Okay. Arctangent of negative 1 over root 3. Again, it's negative. So where do negative ratios of tangent exist? In the 4th quadrant. Opposite over adjacent, so that's 2. And again, think about, what is this angle? Well, this is a 30-degree reference angle in quadrant 4, but remember, I don't want the large angle. The way that tangent's been defined is from negative 90 to positive 90. So this 30-degree angle is actually negative 30 as a principal value, or negative pi over 6. Okay? Inverse cotangent of negative 1. Okay, again, think about, where is cotangent negative? Cotangent is negative in quadrant number 2. So I'm going to draw that. I need an adjacent to opposite to have a 1-to-1 ratio. So 1, 1, this is root 2. Oh, that's a 45-degree reference angle. But remember, in quadrant 2, cotangent's been defined from 0 to 180. So that 45-degree reference angle is really 135 degrees, or in radian mode, 3 pi over 4. Okay, and as you start to get the hint of it, or the hang of this, my suggestion is maybe like pause the video and solve the rest, right? See if you can finish the rest of them, and I'll work through the solutions. So again, arcsecant of 2, so positive, so there's no ambiguity. It's in quadrant 1. 2, 1, this is root 3. It's a 60-degree reference angle, which is pi thirds. Arc cosine of 0. Well, I have to know that the sine value of 0 happens right there at 0 degrees or 0 radians, or you try to draw a triangle 0 over 1, that just collapses down, so my angle is 0 or 0 radians. Arc cosecant of 1, again, you can think about positive, a 1-to-1 ratio. This is again of our fake triangles, our imaginary triangles, or realize it's a quadrantal value, and it's at 90 degrees, or pi over 2. Again, negatives. That's where students are going to make a mistake. So you have to know your geography. Cotangent is negative in quadrant number 2. Cotangent negative root 3 to 1 would be that ratio. You can imagine that's a 1 there. So put a 2. That's a 30-degree reference angle, but it's in quadrant 2. So it's 5 pi over 6 would be the obtuse angle that I'm looking for. Inverse tangent, when it's negative, goes in quadrant number 4. And it's a negative 1-to-1 ratio, root 2. So that's a 45-degree reference angle in quadrant 4, but the way the principal angle is defined for inverse tangent is make it negative pi over 4. Two more. Negative root 2 is my ratio of secant. So secant lives in quadrant 2 when it's negative. Root 2, negative 1, that's a 1. Again, that's our familiar 45-degree angle, but in quadrant 2, it's 135 degrees, or 3 pi over 4. And then negative root 2 over 2, again, you might recognize some of these ratios. Well, that would have come from a 45-degree angle down here, 1 root 2, make that one negative. Without being rationalized, it would have been negative 1 over root 2, rationalized as negative root 2 over 2. Either way, because it's in quadrant 4, and inverse sine has been defined as a negative answer there as its principal value, you get negative pi over 4. Okay, so that's kind of like just a quick crash course in the geography of the inverses. The actual math shouldn't be new. We've done these ratios in the previous chapter. It's now keeping them straight when they're negative in terms of where do the principal ones live? Where is there no ambiguity when I draw that angle that has that ratio? Okay, so hopefully that made sense. You could try some of the homework that's on the calendar. The good news is that we're on this topic for a couple of days. Come in for questions and we'll continue work with more examples.